Today we have the simplest content in mathematics. Of course, still much simpler content is also available. Sometimes this numerical mathematics you will all feel comfortable. No? We'll see the essentials based on our past gate questions. I am not simply taking questions from our past gate gate CGH alone. I am taking questions from the relevant other questions. I have taken questions from aerospace, mechanical, civil. So wherever I find relevant questions based on our past gate question papers. No? So this summary or digested contents I am giving it here. Here in this matrices, these topics, simple topics like multiplication, transpose, determinant, then what is it, inverse, and something about this symmetry, symmetrical matrix, and orthogonal matrix. So these aspects, then followed by rank of a matrix, then eigen values and eigen vectors, then the solution of equations. So all these topics are part of your gate mathematics content. Okay, so these essentials based on the past question papers and collections from various others gate questions, I am giving it to you. Okay. Okay, to start with, let us see the essentials of matrices. Okay, matrix multiplication, you all know this. We need to have this consistency, or is what is it? If you have a m into my n to be multiplied with n, or is this number, no, this should match this row multiplied by column and column multiplied by here also again, row and column. No? So is this this numbers should match. Okay. Whereas 2 by 3 can be multiplied with 3 by 2. So that way only you can do, no? So that and all you should, at least you are aware still, we need to recollect that. And for example, this small example is given here. As I said, 3 by 2 can be multiplied with only 2 by 3 to get 3 by 3. So here, how this multiplication with reference to a 3 by 3 matrix, 3 by 3, again, sorry, this is 3 by 3 and this is 3 by 4, you will be getting 3 by 4, no? So how to do that? This multiplied by this, so that will be coming as a single number. So this multiplied by this row multiplied by this column, so of course the corresponding element, this corresponding element are multiplied and everything is added and a single entry is available. So of course you know that. And for transposing, so whatever the row will be coming as a whatever the column will be coming as a row, otherwise row will be coming as a column. So normally this column you can write as a row. So okay, this is a transpose and something about what is called a symmetric matrix and skew-symmetric. So for this symmetric matrix, A transpose, always transpose of the matrix will be also equal to the original matrix. And here the another terminology what is called as skew-symmetric. So for which A transpose will be minus of A. So in that case, actually this diagonal elements will be simply 0. Okay. This whatever the contents, no, a kj equal to a jk. So the minus of, whereas here it is the same. So this terminology you are supposed to know. The example is given. And something about triangular matrices. Now, these triangular matrices are very helpful to solve. And sometimes, wherever there is a lengthy matrix available, we'll try to reduce to simple diagonal matrix. So once it is available as a diagonal matrix, we can easily solve them because it is at last they are matrices are to solve linear equations. No? So we are actually reducing, converting the equations so that at last only one variable is available, and once that variable is solved and another that variable value is available and you can get the other variable. So by that way you can easily solve them. Okay, so in that way this triangular matrices, so this is what is called as upper triangular. There is the over this over the diagonal, of course from the diagonal onwards, here we have the entries and the lower part are 0 0, everything is 0 matrix. This is lower triangle, or is below and the diagonal we have these entries. Okay, so these are all very helpful and we can easily take the determinant for this kind of triangular matrices. Okay, that case triangular will be this determinant will be simply the multiplication of these diagonal elements. No, in that way they are very simple. And also for solution of equations you need to have this it in triangular form. Okay. And other names also you should know, the identity matrix, and in the case of zeros, matrix of zeros, entire elements will be zeros. And what is called as a scalar matrix, that is here in place of one it can be any other number, that is scalar matrix. And diagonal matrix refers to entries only in the diagonal elements. Diagonal elements are having only non-zero. It can be zero, of course. The other elements are simply zero. Yeah, some these rules also you are supposed to be aware of. You can have this AB which is not equal to B. You have to this order of multiplication that matters. Okay. Of course, this associative law is available. So A multiplied by B into C, otherwise AB multiplied by C. This is okay. And like that, these distributive laws are right there. Otherwise, this rule is very important. You cannot do this. Uh, Otherwise, A multiplied by B is not equal to B multiplied by A. Okay, because dimension wise they won't match sometimes. Okay. Otherwise, also this is very important. Okay. So, and determinant here, determinant of A B equal to determinant of A into B. Sometimes these and all, sometimes you may feel it tough to keep it in mind. In that case, you can work it out for the problem concerned. You can see that. So, not a problem. So, and one of the simplest thing you can keep is determinant of A transpose is simply equal to determinant of A. So, this is this can be kept in mind. And if two rows of a matrix are equal, then the determinant will be zero. And also we'll say like rank is zero. So there is a related thing. We'll see that as part of rank and equations and all. Okay. And if your row is having all the zeros, then of course determinant is zero. And as I said, triangular matrix, the product determinant is simply the product of diagonal entries. Okay. This eigenvalue, so which is a common question. So for taking the eigenvalues, for getting the eigenvalues, we will do this operation. First thing is the original matrix, what is given A, and that will be subtracted with the identity matrix multiplied by this eigenvalue. Eigenvalue. So is A minus lambda. This I is now simply the size of identity matrix matching with the size of A. Okay. Like that. And of course, this eigenvalue is simply a scalar number. It can be a complex number as well. Okay. So that is multiplied and the overall content will be taking a determinant and equate that to zero, and we'll be getting the values of lambda. So they are nothing but the roots of this equation, and based on that, sometime to get the eigenvalues of powered matrix, or say A power n. So for that, the eigenvalues are simply whatever the eigenvalue you are getting here, and that will need to be taken the same power. Suppose it is A inverse, and here it will be lambda 1 inverse. So lambda 1 inverse, so that means 1 by lambda 1, that way. So by this way, you can easily get the eigenvalues of any other, of course, any matrix which is having a power of this original matrix. This n may be even positive or negative as well. Okay. And for this to get the eigenvalue, there are also some simple two relations helping us. So the sum of the eigenvalues are simply the trace of A, which means the sum of the diagonal elements of the A. So original matrix, the diagonal elements, simply add the diagonal elements and to get the sum of the eigenvalues of the matrix, given matrix. Okay. And like that, there is also additional relation. The product of eigenvalues, or is simply the multiplication of these eigenvalues, is simply equal to the determinant of the given matrix. So these two will help us a lot sometime to simply get the eigenvalues based on so whatever the bigger matrix you have, we can easily do this operation. No? Okay. And if this matrix is giving eigen value as a complex number, then the inverse matrix will also have complex eigenvalue. The original matrix, if it is giving complex number as an eigenvalue, and the inverse matrix will also has complex eigenvalue. Okay. And if the eigenvalue is complex, the related one, what is called as eigenvector, is also complex. So these are all something. And rank, of course, for getting the rank, we need to check for the determinant. If the determinant is equal to 0, that means the size is to be lesser than or is related. Okay, if you are having a 3 by 3 matrix and if the determinant is equal to 0, that means the rank is not equal to 0. It is not equal to 3. It is less than 3. For that, sometime if you are having a bigger sized matrix like greater than 3, or say like 4 by 4, or even for 3 by 3 also, sometimes we cannot easily take the determinant. Instead, we'll be converting the determinant into converting the matrix into simply diagonal matrix. So for that we'll be doing this row operations, like adding two rows or multiplying one row with another, and that way, not multiplying one with another, or is multiplying one row with some scale, some numbers. So by that way we'll be doing some what is it, row operations, elementary row operations. So for the elementary transferred row matrix, still the rank is the same. Okay, always row equivalent matrices has the same rank, have the same rank. Okay. So this how this row reductions are done. For that I have some at least one or two examples available. We'll see them. And for this solution of equations, of course, the entire matrices we are using at last to solve this linear set of equations. That is in our chemical engineering perspective. Whereas this image processing and all, they are also using this eigenvalue, eigenvector related contents. Whereas essentially for our chemical engineering, at least we have seen for this solving this kind of equations. There is this kind of equations are quite common. Sometimes they also say what is called as another equation, what is called as ax equal to 0. This b will be simply 0. So these equations are called as homogeneous system of equations. Of course, in differential equation also, wherever this right hand side is coming up, so we'll simply call it as homogeneous equation. Okay, we'll again discuss that in differential equation part. Okay. Here we also see get some solution what is called as by default x will be 0, otherwise x is a vector here, A is a matrix. So vector means one dimensional. Okay, okay, otherwise there will be a column vector. Say here, mm, uh, uh, by default x equal to 0 is a solution for this equation. And to get something called as non-trivial solution, so how to under what condition you'll be getting non-trivial, so that and all we'll discuss. Okay, by the way of some problems. Okay, these are the essential topics for our thing. And additionally, one more thing, what is called as orthogonal matrix. For that I have a problem, we'll discuss as part of that. Okay, so now the initial about 20 minutes will be very simple content. Okay, at least to help you to recollect whatever your school mathematics. Okay, of course, these are also being asked. This question from this agricultural engineering. Okay, so AG 2024-36. Of course, for a 2 mark they have asked. So let us see. So this this problem involves matrix transpose as well as multiplication. So we have this what is it? 2 rows and 3 columns. 2 by 3, and this also 2 by 3. Correct, no? 2 by 3, 2 by 3. Of course, as such, you cannot multiply this, and they have asked for this P transpose to be multiplied with Q. Service, we need to first get the transpose of this P. So transpose will be, again, this is 2 by 3. So transpose will be simply 3 by 2. So this 3 by 2 and 2 by 3 can be multiplied. So result will be definitely, so this is 3 by 3 matrix we should get. Okay, because it is uh yeah, no, of course 2 by 3 is now going to be turning to 3 by 2, that is going to be multiplied with 2 by 3, so you'll be getting 3 by 3 matrix. Okay, that is the very minimum thing first we are supposed to know. Okay, how the multiplication is to be done. Of course, all of you know, still I'm taking it because even I figure I was having difficulty sometimes to recollect this multiplication also. Okay, in that way, I have taken this problem. Maybe for you, it may be a very silly problem. Okay, still. So we have this, how to take the transpose. Simply take this column content into row. Okay, this second column a second row. So in that way you'll do this, and this we have this 2 to be multiplied. So this and this will be the single content. So 2 into 8 and 4 into 12. So they are the single content, like that, this multiplied by this. So 2 into 11 22, and 4 plus 4 into 6 24. Okay, so by this way, first you will multiply this. Okay, then take up this. Okay, by this way will be forming the second row, and third row will be this. Okay, by this way you'll be getting this uh, multiplied content. Okay, so you can easily check the answer. Okay, I think 128 and what is it, 70. So these are all matching to this number. Okay, very simple, but still at least from the start I can give, no? So that I just give. And again, 2 by 2 inverse for 2 by 2, all of you are very comfortable. Okay, still we'll see. This is taken from this petroleum engineering. Petroleum engineering is also, of course, has some chemical engineering content, but more of civil and mechanical they are learning. So in that way, some questions I am taking even for our thermodynamics or sometime some related simple topics. Okay. So for this 2 by 2 matrix, which is given here, what is a inverse? So of course, all of you know this inverse is simply 1 by determinant of the constant matrix multiplied by adjoint matrix. Okay. So and for this 2 by 2, we have a simple thing. We don't even worry about what is adjoint and all. We'll simply whatever the given matrix you interchange. This number 1 and 2, you put it here, 2 and 1, interchange these elements, and for this the other diagonal, always this is a primary diagonal. Okay, for this primary diagonal simply interchange the elements, and for here you change the sign. If it is positive and make it negative. So that is what is given in this diagram, no? So this interchange these elements A and D and change the signs of C and B. So by that way you'll be having the adjoint matrix that has to be divided with the matrix determinant. Okay, so what is the determinant here for this given matrix? So 1 multiplied by 2 minus, here you will be having minus 3 into 1. So okay, this is the determinant. So this determinant and this multiplied 1 by determinant multiplied with the adjoint matrix, you will be having this. Of course, we can also verify this A multiplied by A inverse should lead to a identity matrix. Maybe sometime you can verify your answer easily. Fine. Yeah, sometime 3 by 3 will involve more. 3 by 3 again, you can also use the same thing, less 1 by a determinant and getting the adjoint matrix. So for adjoint matrix, there are many things to be done in this 3 by 3. Of course, instead, we can do this simple elementary row operation to get this inverse. So that thing only I'm going to discuss. So the very detail like getting using this adjoint matrix, that is useful, but sometimes we may miss something, and the sign is to be properly taken care. Obviously, you'll be having plus minus alternating signs, and sometimes if you do mistakenly, it will be totally it will be wrong. Okay, instead. You can follow this simple elementary row operation technique, so that I will help you. So we have this simply a simple diagonal matrix. So because these elements are 0. So for this, what is a inverse? Now, of course, we can also simply check with the one matrix with another thing and multiply it and look for A. Yeah, AI will be equal to I. So whatever the matrix you have, if you multiply with and if you are getting it as A inverse equal to I. So you can also do that way. But that and all will take some time. If of course, luckily here the many elements are 0, you can easily do. But still, so let us see this elementary operation how it can be used here. So you can have this adjoint matrix, so simply the whatever the A given matrix, and have this the corresponding size identity matrix. Okay, and do this elementary operations. By that way, you try to convert your matrix to a identity matrix. So whatever the matrix you are having, okay, you try to convert that to a identity matrix, and you will be having this already having a identity matrix to start with. Now that will be equal to actually the inverse matrix. So starting with this what is called as this is I forgot that. What is it? Adjoint matrix. Oh, yeah, adjoint matrix. So adjoint matrix. So whatever the original matrix and having this inverse matrix, and from that, if you keep on do the elementary operation so as to make the given matrix as a identity matrix. So in that way, whatever the of course whatever the operations you are doing, it is also done to the other matrix as well. Okay, only the elementary row operations will be doing. Okay, so by that way, we are trying to make this first matrix original matrix as a identity matrix. So in that way, this other matrix will be turned to the inverse. So you can either have it as I am starting with A followed by I. You can also have it as I followed by A, whatever the thing. Okay. So in that way also, if you start with I here and you will be getting a I in the other side. Okay, by that way, uh, you'll be getting the same thing. Okay. So let us see how it is done, how the elementary row operations are done. Okay. So row 1, is our thing is these elements to be made as 1. So any other elements are there here, that should be, is only the diagonal elements are supposed to be 1. So first let us see these operations so that here we don't have much elements. No, there is more, most are 0. So in that way, our target is to make these numbers now as 1 simply. Okay. So for that you can easily do this first thing, how to make it as 1. You make it as multiply this content with 5 and as like this multiplied with 2. So as row 1, that new row 1 is original row 1 multiplied by 5. So in that way these numbers are changing. Okay. This is simply 0 0. So this number is now changing to 5. And row 3, which is having this 0.5, now we make it as 1 by multiplying with 2. The same way it is also done here. Okay. So in that way, this element is now turning to simply, these are all now becoming identity matrix. As the given matrix is now turning to identity matrix. So this is going to be the corresponding inverse matrix. So this simplest row operations you can do. Of course, here it is easily coming because of many elements are 0. Uh, so otherwise also you can you'll be able to get this what is it, this kind of identity matrix for the original matrix easily. Okay. So I feel this method is much better. Or is without any memory or anything you can do, no. Whereas this adjoint matrix, sometime we may miss the signs and all. Okay. So we'll move to the next. The determinant of a 3 by 3. Of course, all of you know that still. So how it is done? So for this, say first element multiplied by these contents. So this multiplied by, okay, this into this minus of this. Okay. And for this, you'll be taking minus sign. Okay. Minus of whatever the content here. And that for this, the elements are, of course, you have to keep this, no? And this multiplied by this and minus. Okay. So 2 multiplied by 1 and 3 multiplied by 0. And for this, the third element will be kept as such. Of course, if it is a 4 by 4, how it is done? Plus minus plus minus also should be there. But to that level, 4 by 4 and all, they are not asking, but there is also an example available. For that, of course, we can also use again elementary row operations. So we'll see that with another example. Okay. Yeah. Yeah, let us see how this row element operations also done. Okay. So here, so we are going to do this row operations. At last, if the elements are if the matrix is made to a diagonal matrix, not a diagonal matrix, or is a triangular matrix. Diagonal matrix means only the elements in the this diagonal alone. The other elements are to be made as 0. Whereas it is enough to make this as a triangular matrix, the lower triangular or upper triangular, whatever. Okay. So by that way, you can simply multiply these diagonal elements to get the determinant. So for that, let us see. So what can be done, or is we are aiming for, okay, making these lower elements to 0. So for that, yeah, this is the original given matrix. So you can do this operation like row 3, the new row, or is you want to make this as 0, or is this element, at least first element will make it as 0. So for that, this row 3, original row, this new row 3 is equal to the original row 3 minus 3 times this content. So by this way, now this number is turning to 0. Of course, we have now some more thing, this also to be made as 0. So for that, prior to that, we'll also do something for the row 2. So row 2, there is a new row 2. Or is left side is new and this is old content. Okay. So old row 2. Old row 2 is this 2, 1 and 0 are there. That has to be subtracted with minus of. This idea is we want to make this, at least this element to 0. So by this way, now this is also made to 0. Now you can do operations with these two to make this 0. So row 3, is row 3, original row 3 minus twice of this. Okay, by that way, we'll be making this 0. So now this is coming as even along this, we have tried to make this as 0 so as to get a diagonal. Along this also now becoming 0. That means actually this original determinant is actually coming as 0. Simple, no? So in that way, actually this is, we also say this having a rank of less than 3. Rank of 3 means all the rows should be at least, there should be no full rows of full 0. Okay. So here, since it is row of full 0, so it is having rank of less than 3. And for rank to be less equal to 2, at least there should be one 2 by 2 content with non-zero row. Of course, here it is. The rank is 2. Okay, we'll see that as part of rank. Still, I am saying that this is having rank less than 3, of course, equal to 2. Okay. And now we have this determinant is coming as 0. Okay. So determinant is simply the multiplication of the diagonal elements. To make this, make it as a triangular matrix, we can do this kind of elementary row operations. But again, there are some restriction on these elementary row operations. There is normally for solution of equations, we can do variety of operations. Of course, what sort of operation we used to do in place, we also interchange the rows. Sometime to make it as a diagonal service, if this is easily going to 0, sometimes we'll shift this also. That row shifting and all, if you are doing, you should be very careful, at least in the determinants, getting the determinants. Whereas for solution of equations, you can do variety of row operations, whereas for determinants, there are some restrictions. Okay, we'll see that with the example as well. So at least you can do these simple row operations. Otherwise, the usual row operations what we do. No? This whatever the row 3 minus the multiplication of the row, okay, or the plus or that kind of thing operations you can do. Okay. So we'll see with other examples. So here it is a very simple matrix. We have this, of course, 5 by 5 appearing to be lengthy, but luckily simply diagonal. This it is a triangular matrix, so you can simply multiply this. Okay. So in that way, the problem is very simple. Okay. These were asked for a 1 mark. Okay. Fine. Yeah, this very recent question we'll see. Of course, appearing to be something complex, but you should not worry. If you are able to understand these notations here, then it is problem is done. So what is given here is we are given with a square matrix. Only for a square matrix we'll be taking the determinant. We'll be able to get the determinant. So elements of this A, the matrix are given, which is I used to write now Aij, row followed by column. Okay, this Aij is simply equal to I multiplied by j for I greater than or equal to j. Okay, what is the meaning of that? So I refers to this column and correct no? Yeah, I refers to yeah, there is 1, 1, 1, 2. Yeah, this is I refers to column only. Okay, right. I and j, this is yeah, sorry, j is sorry, I'm trying to confuse you. Okay. Say, of course, I have written it correctly. Okay, no worry. Simply, what is this saying? This for I less than j. Have I written this correctly? Please check it. A11. Say what is, let us first write this 1, 1. So there is I greater than j. So here what is j and I are the same. First, that is simple, very simple. And here A1, 2, no? This is A1. There is row 1. Okay, row. This is actually referring to row number. Okay, and this is column number. So A1, this is A12. So A12, what is the A12? This is now this J is, unless I is greater than J. Have I written properly? Please check it. Okay. Please check it. Check it. It's written correctly only. Okay. And we'll be having this matrix. Okay. So what we are getting is a triangular matrix. Simply, you can simply get the this what is it? Determinant. Simply this multiplication of the diagonal elements. So for that, we are having these diagonal elements as these numbers. Okay. So you have to multiply them. So you can again group them, and this is n factorial. N factorial is n into n minus 1 into up to 1. We'll write, right? So the same way here also, the other the same content repeating, and this is n factorial multiplied by n factorial. So this result. So this is appearing to be a little tricky. Okay, simple only. Okay, for a 2 mark, we can easily get this. Okay. So here there is another interesting thing also. What is called as sometime there is a matrix available, and there is another matrix which is simply a scaled matrix. What is called as a scaled up, scaled down matrix. So for one of the matrix, there is for the usual matrix, for a matrix the determinant is given, and for the another scaled matrix you are asked to report the determinant. Of course, without worrying, also you can get the determinant and solve the problem, but it will take time. So since it is only actually 1 mark question, for 1 mark you should be in a position to get the answer in a minute, less than a minute. So for that there are some simple thing, no? So what is that? First, okay, let us see what is the thing connection between these two. So this is the matrix for which we need to get the determinant. So the original matrix is here, and this comparison you can simply see this is this multiplied by 2 is the this matrix. Okay, so for this, okay, suppose you are trying to do this in what is it, determinant. So you can multiply this and this, then okay, by this way you'll be getting this. Not a difficult thing, but still. So what is the thing we are getting actually? This simple rule is available. So determinant of a scaled matrix with a scaling factor of alpha, that is equal to this alpha times n. Say otherwise what here it is said, the matrix is scaled by 2, okay, and 2 to the power 3. Why we are making it as power 3? So power 3 is because of the size 3 by 3 matrix. Suppose you are having a 4 by 4 matrix, okay, so it will be this what is the scaling factor? Scaling factor is alpha, and what is the size? The square matrix, that is 3. So scaling factor to the power the size, so that is to be multiplied to with the original determinant. Now you should not simply multiply with the 2, because it is suppose it is minus 12, and the determinant you cannot simply write it as minus 24. That is a wrong answer, because so every element is actually multiplied, and actually we are multiplying this here again multiplied by 2. So that means this 2 to the power 3 is a scaling factor multiplied to the power 3. That is important. So scaling factor is alpha, and that is to be multiplied 3 times for the 3 by 3 matrix. So in the case of 4 by 4, you will be having actually these elements multiplied by 4 times. Now in the case of 5 by 4, we have seen these elements are multiplied. No, every element is totally actually there is a 5 times getting multiplied. So in that way, there is a 3 times getting multiplied. So that's why this number 3, or it is a 4 by 4 matrix, it will be 4. So this simple rule you can recollect. Okay, Risk, don't simply do this operation like this is minus 12 and it can be minus 24. That is a wrong thing. Okay, the reason is because every element is multiplied. Okay, and you'll be having this contents coming to the power 2 power 1 2, or else you are having this the scaling factor to the power n will be coming for the determinant term. Okay, that is very important. Okay, now let us see how these row operations are done to get a 4 by 4. So this is appearing to be a simple 4 by 4, but if you try to do by usual operations, so what you are supposed to do, this element multiplied by this 3 by 3 matrix, and minus of this element multiplied by whatever the corresponding elements are, is you have to miss out this and get the other elements. So by that you have to do a what is it? The 4 times multiplied by 3 matrix. So that level of operation is needed, that you cannot do. So you can do this, convert this matrix into a triangular matrix. So for that, the row operations. So let us see the row operations. Of course, simply this minus row 4 minus row 1. So by that way, I am getting the new row 4. So by that way, I am making all this. This you can easily subtract. So that operation is allowed. Okay, so by that way you can subtract or add this combination of rows you can easily do. So there is a permitted row operations, of course. This whatever the row, the new row is the original row. This also you can multiply or divide and add with another row, not only with another row, another 2 3 rows, so you can add. So you'll be having kind of a linear combinations. Okay, these are all the operations allowed. So for this, this row new 4 row R4, we are making it as these things are near as 0 simply by subtracting with this. So by that way, I have this now. Now again, this can be done something for that. R2 is new R2 is simply the original R2 plus R1. So by that way, this and this can be combined to make it as 0. Like that. Of course, I should have done something, no? How this actually it is not simply R2. Even this R3 also, that one operation has been done, which is missed here. Of course, R2 I have written. R2 is this thing. And what about this R3? That this also I have to write one statement here. Okay, that I will correct it and write it. Okay, of course, one another operation for the row 3 also done. So row 3 and this simply add this row 3 with row 1. So in that way also you'll be getting this getting element. Otherwise we'll write it here now itself. So row 3, which is simply equal to original row 3 plus row 1. So the same kind of operation is also now done for this row 3. So this whatever the elements here simply add. So by that these two are made as 0. And so now we have what is it, triangular matrix. So now we can easily do this multiplication, get this. Of course, what are all the permitted row operations? So this row interchange, if you are doing, you need to get the final value. Whatever the determinant you are getting, that has to be multiplied with -1. I suggest better not to do this kind of operations. So this operation usually what we do. So the for a row j, so original row j plus any combination of this row k multiplied with a factor. So these are all not affecting anything. So always the the final determinant is as such is applicable. Whereas if you do this kind of operation, like the jth row is the original jth row divided by or multiplied by, if you are dividing you should get this net result has to be multiplied. So these and all to be taken care, but I suggest only to use the usual simple row operation. Okay, don't do this kind of interchange. With equations that is always applicable, because simply on the equations rearranging here the this for determinant that should not be done. Okay, of course, if that can be done with this kind of multiplication. That is, once you get the determinant, later you should also multiply that with these factors so as to get the determinant of the resulting matrix equal to the original matrix. Okay, so they are needed, but I suggest only to do with this uh, elementary permitted row operation. Okay, that you won't miss anything. Okay, okay, now. Again, to simply recollect about this transpose inverse, I have a very simple question here. So this simple 2 by 2 and the transpose is, okay, what is this? Simply, what is it, row is made as column or column is made as row. Okay, so here we need to validate the statements. So given statement, what are the, which is the correct statement? Okay, Q is equal to its transpose. That is not correct, because Q and Q transpose are different and equal to its inverse. So that means, so the transpose, sorry, whatever the Q is equal to its inverse. That also we can get for that. What is Q inverse? Q inverse is, so whatever the given matrix, and take the determinant and make the adjoint matrix. For that, simply swap the entries and change the signs. Okay, so in that way simply whatever the things, these are all, this -2 will be +2 and this will be minus. Okay, whereas these two elements are the same. So by that way we have this inverse, and this q and q inverse are not the same. Of course, q and q inverse will be same only for, I think, identity matrix, no? Okay, maybe I don't know whether any other things are there. So this kind of properties checking and all not very because these are all mathematicians content. Okay, we are not very comfortable in that. So and what about these other statements? Q is equal to its transpose wrong, and equal to inverse wrong of full rank. So full rank means this determinant should not be 0. So here the determinant is not 0 already. We checked that. So in that way, uh, all the two rows are essential. No, you cannot. Otherwise, no row is coming as full 0, or no column is coming as full 0. And what is the other statement? Has linearly dependent columns. Now, whenever the rank is less than the size, then you'll be having linearly dependent columns. Okay, dependent columns as well as rows. It can be columns or rows. It doesn't matter. So there is no linear dependency. Okay, otherwise these are all the elementary contents of mathematics. Now we will see. Yeah, of course, some more problems are there. Okay, let us see. Yeah, we'll be in a position to finish everything. Maybe another 2-3 contents. Then we'll take a short break. Then we'll see the rest. Okay. This we have seen. What is called as symmetric and skew-symmetric. So we are given with there is a square matrix, and when it will be a skew-symmetric. So for a symmetric matrix, that the transpose is simply equal to the original matrix. For a skew-symmetric, okay, this transpose is equal to minus of the given matrix. Okay, so here it is skew-symmetric. So transpose is minus of the given matrix. So this is the correct thing. Whereas this is the correct thing for simply symmetric. So this is actually valid for skew-symmetric. Of course, this is also not this is. Of course, there is another matrix what is called as B inverse is simply equal to is the transpose is also equal to inverse for a matrix what is called as orthogonal matrix. For a orthogonal matrix, you can easily get the inverse simply by the transpose of the matrix. Okay, I think that statement we'll see it along with what is it orthogonal matrix. So for symmetry, okay, this transpose and the original matrix are the same. Of course, you can see that, no, how this is valid. So there is this row, column will be becoming as a row, no. So you can see that this for the transposed matrix, of course, this column will be becoming row. So in that case, of course, if you have these elements, they are valid. That is, whatever the element here, that should be the element there. The diagonal element can be anything. Whereas for the Q symmetric, you should make this matrix transposed matrix will be equal to minus of that. So for that, if it is having these signs, opposite signs, okay, then they are okay. And in that case, it is necessarily this diagonal elements are 0. For a Q symmetric, the diagonal elements are 0. So only then you'll be having this transpose equal to minus of that, because 0 plus minus doesn't matter, no, simply. Okay. Matrix with transpose equal to inverse. As I said, what is called as a orthogonal matrix. So for the matrix, the transpose is equal to inverse. So for that, what is the value of x? We need to evaluate x, and there is a statement. Otherwise, for this matrix, uh, the inverse is simply equal to the transpose. So you can easily get the inverse simply taking a transpose, and we know one simple rule A in inverse is here M inverse is simply equal to I. So any matrix multiplied with the corresponding inverse matrix is equal to identity matrix. So by that multiplication, we'll be getting a we are supposed to get a identity matrix. So in that there will be a uh, entry with x. So we can equate that entry to 1, and by that we can solve it. So what is the original matrix? And it is given that identity matrix, sorry, M inverse is simply the transpose which is given, of course, which is valid for the diagonal matrix. Okay, what is called as a diagonal matrix. Okay, diagonal, sorry, not diagonal, what is called as orthogonal matrix. Okay, so these statements, please. So for a orthogonal matrix, inverse is simply equal to transpose. Okay, so now you need not worry about this. So simply whatever the statement is given, you do that. M inverse is now simply M transpose. So and we know one rule which is always valid. So the matrix multiplied by its inverse is equal to identity. So by this you are getting a entry, and we are supposed to get, we will be getting entry relate to, in terms of x, so that has to be equal to 0. So by that, by equating that, you will be getting that. Okay. And as I said, for a orthogonal matrix, transpose is simply equal to the inverse. And there are also some more additional thing properties, what is called as the determinant is simply equal to plus or minus 1. It can be plus 1 or minus 1. Only these two values are possible for a orthogonal matrix. And it is also the dot product of any two different rows or columns. Suppose you have two, three rows and columns. Okay, this one column with multiplied with the other column. That dot product of this thing, or is suppose A11 multiplied by with the other, that is the corresponding entry in the two different rows or columns. If you multiply and get the total thing, that is equal to 0. Okay, that is this also a rule for applicable for this orthogonal matrix. Okay, we have also one more example related to this orthogonal in this eigenvalue eigenvector topic. Yeah, this solving simultaneous equations. As I said, you try to make this as a diagonal matrix. So whatever the matrix given, you do these operations for that, not diagonal, what is called as triangular matrix. Of course, diagonal matrix also a triangular matrix, which is having both upper and lower as zeros. So now we look for only making any of this thing, simply upper or lower triangular matrix, that is enough. So for that, you can do some row operations. Otherwise, so this can be interchanged with this. We take this equation and put it. Suppose you have some four, five equations and simply rearranging it. That operation is always allowed. Whereas only for the determinant, if you do this interchange of rows, you should this take this sign. One interchange, that means there is a negative. That is also there now, because in determinant we used to say the plus minus, that cofactor matrix and all. Now we'll be writing that plus minus. So that kind of plus minus things are not there with reference to equation simply. Okay, simply this equation is taken prior or next. So by that way, of course, this you need not worry. This vector will be the same. Whatever the operation you do, this vector will remain the same. Okay, that also you can verify yourself. Okay, so by this way, you can simply change these rows and everything. Okay, without worrying about this. Of course, if you do this, the same thing is also applicable here as well. That is, whatever the entry here is shifted by one or by any other thing. Okay, so that operations we are going to do. So for this augmented matrix, now this operation is done. This row 1 and 5 are interchanged. Somehow we have to make it as a triangle. Okay, so for that, this element, of course, now this also there. So of course you can also still solve, but comfortably if you make this also as 0. So this element, which is the fifth element, so this multiplied by x5 will be directly giving this answer. Okay, once this is solved, and the using that you can now solve for this x4 and x3, that is what is asked. So these are all possible only if you have a single content, for the last row. So otherwise also you can try to solve. Of course, 5 by 5 means you have to write as a 5 by 5 matrix, take the inverse and solve it. With a computer you can solve that. For hand calculation, only one or two variable at the most can be solved. After then, these are all taking inverse and solving it. So this eigenvalue is an important topic here. So for that, we'll do this simple operation, what is called as, so otherwise we are essentially going to solve for lambda. So for getting this eigenvalue, we are making this simple uh, estimation of determinant, which is the original matrix minus the eigenvalue multiplied by identity matrix. That means simply this matrix subtracted with a scaled identity matrix. Okay, this scaled by this value. Of course, eigenvalues are, again, if it is a 2 by 2, you'll be getting 2 eigenvalues. So if it is a 3 by 3, you'll be getting 3 eigenvalues. Okay. Okay. So of course, this is simply a number, and it is multiplied with identity matrix. Okay, matching with the size given. So it is a 2 by 2. So you'll be having this identity matrix is also a 2 by 2 matrix. Okay, so this simple thing that is to be, yeah, we have to get the determinant. So by that way, you'll be getting a equation for lambda that we are going to solve, and that roots of lambda is nothing but the eigenvalues of the given matrix. Okay, so for that, so the original matrix minus lambda into identity matrix. So that is A minus lambda I is now available. So always simply these elements, diagonal elements alone, if you subtract with lambda, that is going to be the this net A minus lambda I. For that, take a determinant. Okay, so this you can easily take the determinant at least for 2 by 2, no, comfortably. This multiplied by this minus this. Okay, so by that way you have this thing that is to be equated to 0, so as to get this, we are essentially solving for the roots of lambda. Okay, roots of this equation. So for that, of course, quadratic in the case of a 2 by 2. For 3 by 3, sometime tougher, no, you'll be getting a cubic equation that you have to solve. Okay, minimum at least this quadratic you can easily solve easily. For that, so this quadratic and for that this suppose it is like ax square plus bx plus c. For that we used to write like minus b plus or minus root of b square minus 4ac by 2a. No, that is the root of a quadratic. No, so the same thing we are writing. So this is minus of this b element plus or minus root of b square, which is minus 4 square, which is simply 16, minus 4ac minus 4ac. Okay, by that way, that divide by 2 into a. Okay, a is 1. Okay, this is the thing content we are getting. And this is again plus or minus. So plus and minus of that. So we have these two roots. Here what is given is already there is a eigenvalue given. So the other value only we are asked to report. So for this, of course, you need not do this lengthy calculation also. You can easily do this simply by certain rules applicable for these eigenvalues. Simply, the sum of eigenvalues is equal to sum of the diagonal elements. Hmm. Of course, I also already discussed that thing in the initial notes part. Still, the formula is simply the sum of the eigenvalues of a matrix is sum of the diagonal elements. What is also called as a trace of a matrix. So the diagonal elements are 2 plus 2. That is a sum. So the eigenvalue sum of the eigenvalues, that is sum of lambda is equal to sum of these diagonal elements, which is 4. So already one eigenvalue is 0.27. That means the other thing will be simply the 4 minus of 0.27. That way you can easily report the other eigenvalue without doing this lengthy calculations. So by that way you can work smartly. So by that way you can avoid this and you can earn the mark easily. Of course, it was asked for a 2 mark. 2 mark less than a minute. In 30 seconds, you can answer the other one. This part. That way, very easy to score, at least. So let us see. There is also one more rule, what is called as a product of eigenvalues of a matrix equal to determinant of the matrix. So what is a product of the eigenvalues? Of course, this lambda 1 multiplied by lambda 2. So this and this, if you multiply, what you will be getting? That is actually coming as 1. That is also equal to determinant of the matrix. So what is a determinant? So 2 into 2 minus this 3 into 1. So it is going to be 1. So that rule also sometime you can use. That is also coming here correctly. So this is your value is 1 is given as 0.27. The other is now equal to 1 by 0.27 because this determinant is equal to 1. There is 4 minus 3, that is equal to 1. So this multiplication of this 2, that is equal to the determinant, so which is equal to 1. So in that way, it is simply 1 by 0.27 is the answer. That way you can work smartly. Okay, either by determinant or by sum, both are applicable. Okay, now how to get the eigenvalue for a m cube. The original matrix eigenvalue you can get because the original matrix is given. For this, you can get the eigenvalue, and from this, you can say about the eigenvalue of the M cube matrix. So, suppose we don't know the rule, what we will do, we will be taking this M, first M square, M into M multiplied to get M square, and M square multiplied with M to get M cube. So, then you will try to do, so by that time, your whole of time will be lost. Okay. So, whereas there is a simple rule available. So, for that, first let us do for this eigenvalue of M we will do. So, for that M minus lambda I equal to 0. Simply whatever the elements subtract with lambda. Okay. Then you'll be getting this quadratic and solve for the roots. So minus b plus or minus root of b square minus 4ac. Okay, that divided by 2a. So that is going to give this lambda, which is 16 and 4. And this is the eigenvalues of the original matrix. What is asked is the sum of the eigenvalues of M cube. So sum of the eigenvalues of M cube is simply equal to, so sum of the cube of the elements. Of course, for M, we have this 16 and 4. So for this, the total sum is 16 plus 4 that you can write. But what is asked is sum of eigenvalues of M cube. So that will be simply the corresponding element that is cubed. That is 16 cube plus 4 cube. That is the summation of eigenvalues of M cube. Okay. So that is that simple rule we can easily apply. Of course, here first we should solve for this eigenvalues of M. Once that is available, M cube is simply this each and every element lambda cubed, and totally you have to add that sum lambda 1 cube plus lambda 2 cube. This lambda 1 lambda 2 are eigenvalues of M. So only there is a rule easily do applicable. Always that rule is applicable always. Okay, not only for any always n can be positive or negative as well. That means suppose you want to get the m eigenvalues of m inverse. So this inverse of 16 will be or is 1 by 16. That is 1 by 4. That way you can write the eigenvalues of m inverse. Okay, that is a smart way. Of course, you have to use the rules, other rules. So whatever the m eigenvalue you are getting, if it is m power n, lambda corresponding lambda to the power n. Okay, that way you can easily solve this problem. Eigenvalues again, we are sum of the eigenvalues are asked. So we are having a matrix with unknown always some parameter p is given. So what is the sum of the eigenvalues? One of the eigenvalue is given. So what is the sum? Sum is actually we are going to get three eigenvalues, out of which one eigenvalue is given. So the what about the other two eigenvalues that you have to report in terms of this parameter? Okay. So sum of the eigenvalues, sum of the diagonal elements. Okay, here the diagonal elements are 1, 0 and p. So the summation is simply equal to 1 plus p. Okay, so that 1 plus p equal to 3 plus content, correct? 3 plus the unknown elements. This u is now the sum of the other eigenvalues. Okay, so that is what is asked. So u is simply again rearrange this equation. That is 1 plus p is a summation out of which one element value is available. So that is that means this is also equal to 3 plus the other unknown sum of the other eigenvalues. So by that way you can easily get this for a 1 mark. So this way eigenvalue problems are easy to at least answer. Yeah, similar again to repeat. So for a for a matrix we are given for a 3 by 3 matrix we are given with a trace and determinant. Trace means sum of the diagonal elements. Okay, so and the determinant is available. Value of the determinant is minus 48. Now please note it out. It is minus 48. No, don't simply take it as 48. So this minus is there. Okay, and the trace is 8. Okay, there is sum and determinant of a matrix are available. Sum of the diagonal elements and the determinant of the matrix are available. So from that, you have to say about the eigenvalues. One of the eigenvalues given, the other two values. The other two values, what can be. Okay. So sum of the diagonal element is simply equal to the trace. Sum of the eigenvalues simply equal to the sum of the diagonal elements, which is equal to the trace. So that is given. Lambda 1, lambda 2, lambda 3, that is equal to 8, that is given. And lambda 1 multiplied by lambda 2 multiplied by lambda 3, that is equal to the determinant of the matrix, which is given as minus 48. So using this, of course, two unknowns and two equations, you can solve them. This one of the value is given. So this lambda 2 and lambda 3, you have to solve for. So, two equations and two unknowns, you can solve. At last, a quadratic is coming. You can easily do this. That means these rules are to be known. Only then you can solve this kind of problem. Of course, for a 2 mark it were asked in metallurgy stream. Okay, now this problem slightly will take more time. And this is about orthogonal matrix. So we are given with a 3 by 3 matrix. Which of the statements is incorrect? Which is correct means sometimes we can easily do. Incorrect means every statement has to be evaluated and okay. Normally will take time, more time. So here determinant of p is equal to 1. of course, it is nowhere said about orthogonal. Of course, there is one thing available. Of course, this matrix is going to be orthogonal. That we also will be proving. Okay. So for the matrix, let us evaluate whatever is possible. Determinant of the P is equal to 1. Is it possible? Determinant we can easily do because at least this element is 0. So we can easily do this. So determinant we can evaluate this multiplied by these contents and minus this and okay. So by that way you can do this. So determinant is coming as 1. So this is a correct thing, but we have to say about the incorrect thing. Okay. So okay, that is now that is identified. This is a correct statement. So that means that is not the answer. Okay. So what is what is mean by orthogonal? For a orthogonal matrix, this rule, what is called as the inverse is also equal to transpose, or is P inverse is simply equal to P transpose, which is applicable for a orthogonal matrix. So that we can check. So they also mentioned this inverse of P is equal to transpose. Of course, there is a requirement for a orthogonal matrix. Of course, this statement is correct and this statement is automatically correct. Okay, inverse is equal to its transpose. If this is correct, this is also automatically correct. But we need to say about incorrect statement. Okay, so if one is verified, other thing need not worry, and we have to say about the eigen values, whether it is real numbers or complex numbers. At least this we can easily do. So for this eigenvalue, how do you get the eigenvalue? So simply whatever the matrix minus lambda into I, so that is to be equal to 0. So here of course we have this cubic equation going to come. So this multiplied by this and again this. So this is taking the determinant, right? So for this second thing it will be 0, and again there is again 1 by root 2 multiplied by this. So you'll be having this cubic equation, and again luckily this factor is a common, so that we can group it out. So by that way, of course, lambda equal to 1 is also a eigen value. Anything making this equation to 0 is eigenvalue, right? So by that way, this lambda equal to 1 is also a eigenvalue. But what is asked is all the eigenvalues are real numbers. How many eigenvalues are possible? 3 eigenvalues. So because of a 3 by 3. So the other 2 eigenvalues we need to evaluate. Okay. Again, of course, because of grouping, that we can take it this side, and we are now having this term can be cancelled out. So we are now having a quadratic. For that, the roots are now coming as complex numbers. Of course, complex number always come in complex conjugate. Plus of because of this, the plus or minus will come now. Okay, for the quadratic. So from that, this there are two roots with complex. There are two complex roots, two complex eigenvalues. So this statement is wrong. Okay, so there is a incorrect thing that we can easily say, and these two we can check. So for the inverse, of course, it is given like inverse is equal to transpose. So let us try to do the inverse. Of course, the smartest way is simply uh, the check for take the inverse as transpose and check for this identity whether it is coming. Otherwise, we can do this. So whatever the given matrix, you assume that this thing is correct. Inverse is equal to transpose. So by that way, that is I am taking this first I am taking the transpose, and I am just multiplying this matrix with the inverse, of course, assuming this is the inverse. That is, any matrix with the corresponding inverse multiplied should lead to identity. So since this P multiplied by P transpose is coming as identity, so that means this P transpose is also equal to P inverse. So P, otherwise it is inverse is equal to transpose. That is coming. Suppose you try to do the get the inverse without making this statement to correct. Otherwise either you can do this operation P multiplied by P inverse equal to I by assuming this P inverse is equal to P transpose. Okay. So by that way also you can easily do without much difficulty. Otherwise, whatever the matrix available, you take the P transpose, and now you are equating this P transpose equal to P inverse, assuming this is correct. Okay. And if that assumption to be valid, this multiplication should lead to identity. So in that case, this P transpose is definitely equal to P inverse. Okay, here it is coming, so it is valid. So P transpose is equal to P uh, inverse. So this is valid. So that way also you can prove. But sometime okay, you try to get the inverse and check whether the inverse is equal to transpose. So for that, let us see how this inverse is taken by our elementary row operations. So write the matrix and get the adjoint matrix. So the P and the identity matrix, and do the operations so as to make these elements as identity matrix. Otherwise, this should be identity matrix. So for that, this now should be made as 0. Okay. So for row 3 is what is it? This and this you can add and so make it as 0. No, because these are all easily coming, and this is done, and this again can be made as 1 easily. Prior to that, this let us work on. So for that, the this and this always row 1 can be this row 2 times of this minus R3. So by that way, this element can be made as 0. So now, okay, almost a diagonal matrix we got. These elements and all we can make it as 1 easily by scaling down. Okay. Of course, the scaled matrix, we are now only worrying about this making it as an identity. Of course, these elementary row operations, this scaling are allowed for this rank or solutions. Okay. Only for determinant, you have to be very careful. Whenever you are scaling, the determinant has to be again, whatever the determinant you are getting, that has to be multiplied with the whatever the scaling you are doing. Okay. So now that operations are you can easily do. So simply erase your entire thing, scaling it out or scaling. So we are making it as now this is made as a identity matrix. So this is going to be the inverse matrix. So we have started with Pi. At last we'll be ending up with this is going to be I and this is going to be P inverse. Okay. So in that way, you can easily get this inverse matrix, and luckily this is also matching to the transpose. So in that way, this statement P inverse is equal to transpose is validated, but we have to say what is incorrect. So incorrect already identified, and whenever this is coming, the transpose and inverse if they are equal, so that is valid for a orthogonal matrix. So because of that, this is correct automatically. So more things are done. Of course, our part is about understanding the content. Okay. And one more thing, whenever eigen values are coming as complex, eigen vector is also going to be a complex number. Okay. So that also we'll see in the coming thing. So now we are going to see about eigen vector. Okay. So eigen values and eigen vector for a inverse matrix. So we are given with the original matrix. So for this, uh, what is the for the inverse matrix? What is the eigenvalue or is inverse of a matrix? So for this matrix, we have to first get the eigenvalue. Otherwise, you can take the inverse and you can take the eigenvalue. But no, need not. We know the rules of these eigenvalues. So whatever the eigenvalue you are getting for the original matrix, the for the inverse matrix, eigenvalue is going to be 1 by of that. Or is simply lambda inverse, the correspond lambda to the power corresponding power. Okay. Here it is inverse. So this inverse is -1. Okay. So first let us simply get the eigenvalue for the given matrix. So with for that a minus lambda I equal to 0. Okay, by that we are having this lambda for the original matrix, which is coming as a complex number. Now it is complex number because of square root of minus content. So for that -1 is taken separately, which is square root of -1 is simply a complex number I. Okay, and this is simply as such. Okay, so by that way this is a complex eigenvalue. So what is do we say? Yeah, we have these statements now. So this is a eigenvalue of the original matrix. What is asked is the eigenvalue of the inverse matrix. So for this matrix, the inverse you have to take an inverse for that inverse matrix only you have to say about the eigenvalue. Of course, the eigenvalue of the inverse matrix is simply the 1 by of this content. Okay. So otherwise lambda of A inverse is simply equal to 1 by lambda of A. Okay. Okay. So and if the eigenvalues are real numbers, then the eigenvectors also real numbers. Okay. But here eigenvalues are complex number, then the eigenvectors also going to be complex numbers. So already and one more thing, if the original matrix is complex number, giving complex roots for the eigenvalues, and inverse also will be having complex roots. Okay, because again, if you take a inverse for this also, we'll be getting a complex number. So otherwise, what we are going to get uh, complex eigenvalues. And complex eigenvalues, if they are coming, they are also going to be complex eigenvectors. That is complex eigenvalues and eigenvectors. Okay, this is the correct answer. So because the original matrix is giving complex eigenvalues, the inverse matrix also going to give complex eigenvalues. Okay, that is whenever the original matrix is giving complex eigenvalues, inverse is also going to give complex values. And whenever the eigenvalues are complex, eigenvector is also complex. Okay, these statements are the valid statements. Okay. So, okay, suppose you have tried to do the inverse and try to get the eigenvalue. Let us see how that is also done. So for that, we will take the determinant. Okay, 2 into minus 2, which is minus 4, and this is 4. So this is the determinant of this matrix. And for A inverse, you interchange this and change the sign of that and divide by this determinant. So this is going to be the A inverse. So for that, and now, yeah, whatever the matrix minus lambda I. So by that way, you have this quadratic. So now you are getting this as the what is it roots. Now you can easily see that we are having square root of 12. Here we are getting 1 by square root of 12. Okay, our rule, no? Whatever the rule of this eigenvalue is coming, matching at least. Sometime if you don't know the tricks and all, you should do in a systematic way, no, usual way. So by this way also, but one more thing we should to know that whenever the eigenvalues are coming as complex numbers, eigenvectors will also have complex number. So only then we can say about this eigenvector. Okay. So we need to get this a cube, a square for the given matrix because this term b, which is having this cube, square. So for this, we can easily get using this eigenvalue equation. Okay, that is what is called as a characteristic equation that we'll be getting for this polynomial. So let us see how it is done. So we need to get this b, evaluate this b, which is having these coefficients. Okay, uh, and the determinant of this b we have to get. Okay, so for the a, so we can get the eigenvalue first. So for that, we have this determinant and equal to luckily this a simple quadratic is cubic equation is coming. Okay, and this is the cubic equation we are getting involving eigenvalues. What is asked is we need to get these things a cube a square minus 4a plus 4 5a. Otherwise, simply there is a theorem what is called as Cayley-Hamilton theorem. No? Cayley-Hamilton theorem, which says that the whatever the equation you are getting for this eigenvalue, that you can simply write this lambda with a. uh, Replacing this lambda with a, will be getting an equation. That is the same thing. You can write it for the given matrix instead of this is a scalar, whereas now we are writing it for the matrix as such. So simply replace this lambda with a. Of course, there is a simply a constant that you have to multiply with identity matrix. Okay, because these are all this is a matrix. And this also has to be a matrix. So simply multiply with the identity matrix. What is asked is for 5i, we are getting 4i. So for that, you have to add one more I. That's it. So by that way, we have this B matrix. So B matrix already this content is simply 0. And this, what is the content of this? That is going to be identity matrix. So the determinant of that is simply equal to 1 only. Okay. So in that way, this determinant is already equal to 0. Uh, Okay, and to that we are adding this. This is simply zero matrix, zeros matrix, and this is identity matrix. So at last we have only identity matrix. So for that, what is that determinant? Simple one. So you need not worry about this lengthy equation. If you try to do this, what is it, cube, square, and all, the whole 3 hour will be lost. Okay, we have to be very smart, making use of this simple theorem, Cayley-Hamilton theorem, which is simply writing the characteristic equation involving lambda. Okay, there is from a minus lambda I, and replace the lambda with a. That's it. and the constant term will be again having a multiplication with identity matrix. Okay, so by that way you can get this kind of cube terms. Sometimes this will be exactly matching to the thing, but there will be simply alteration in here or here. So wherever easily doable only they will give this. Okay, so now let us see. Now we are going to eigenvector. So we are having a 2 by 2 matrix. We need to get the eigenvector corresponding. Which one is the matching eigenvector? One of the eigenvector. So how many distinct eigenvectors we can get? There are two eigenvalues possible. So you'll be getting two distinct eigenvectors. Of course, eigenvector you can again multiply and get many number of vectors. Of course, zero by any eigenvector cannot be simply zero vector. There is one rule. Whereas for any eigen matrix, for any matrix, zeros is not a eigenvector. Okay, there is one simple rule. Okay, so always it can be non-zero content. Always all the contents cannot be zero. That is what is a zero matrix, correct? Here, one of we'll be getting two distinct eigenvectors. So we need to get so what is the eigenvector matching to the eigenvector of this. Okay, so a minus lambda I, from that lambda will be getting 6 and 2 are coming. So for the eigenvector x, this equation is valid. A multiplied by x. Sometimes they use this symbol like v also. A v equal to lambda v. Of course, I have used this x for the eigenvector. So ax equal to lambda x. So ax is a matrix, of course, this way. Okay, and this lambda x. So this will be having a matrix, and x is a vector, right, which is having, suppose there are two coefficients means two variables, there is two rows means, okay, two. So x1 x2 or sometimes x and y z, that we also can write. Okay, so this is the equation we are getting now. So from this we can actually, there are two rows and so you can write these two equations, which is, say, 5 into x1 plus 3 into x2, that is equal to 6 into x1. Maybe you can also use this and get another equation also. Both will be giving the same thing. Okay, so what we are getting is x1 by x2. Always, what is the relation between the variables? So x1 by x2 is 3. So this is x1 and this is 2, x2. So this you have to look for the matching options. So this one is this divide by this, if it is matching to 3, then this is here we have eigenvector. Of course, for this we don't have any matching eigenvectors. We also have one other eigenvalue, which is lambda equal to 2. Okay, for this, now let us apply this equation, ax equal to lambda x. So this multiplied by this, so we have this, we are getting this relation, x1 by x2 is equal to minus of 1. So we can scan these contents. So this option B is matching to this. Okay, simply checking for this rule where it is valid. Okay, so here this rule x1 by x3 equal to 3 is not matching to any of the thing. So whereas this rule, which is coming from the other eigenvector, other eigenvalue is matching to this entry. Okay, so simple only. Eigenvector problems also very simple. Okay, so let us see with one more example. So we are having 2 by 2. Of course, 3 by 3 also you can do. Okay, most of the time they are asking this 2 by 2. Okay, so what is a normalized eigenvector? What is the meaning of this normalized eigenvector? Or is this total entry will be equal to 1? In that way, they say like normalized. Okay, no worry about these statements and all. Simply, what you have to get the first eigenvalue, and for the smallest eigenvalue, what is the corresponding eigenvector? So a minus lambda I, from that we have a quadratic and we have this eigenvalues. So let us, for the smallest thing, okay, for lambda equal to 2, let us get the eigenvector. So ax equal to lambda x. So we have this relation, ax equal to minus y, it should be coming. So where is that relation? X equal to minus y. So this is coming. So suppose you have tried this other one, that is lambda equal to 8. So for that, this option D will be matching, but that corresponds to the highest eigenvalue. Okay, so this answer is not correct. So this is the correct answer. So of course, eigenvalue problems you can comfortably work on. Okay, number of distinct eigenvectors. So we're simply evaluating the number of eigenvalues. Of course, number of eigenvalues should be equal to the size of the matrix, size of the square matrix. So here the two roots are repeated roots. So we'll be getting two distinct eigenvectors. Okay, because the eigenvector for this two will be the same, and so you'll be having two distinct eigenvectors. That is, number of distinct eigenvector is simply equal to number of distinct eigenvalues. Okay, in that way you can easily say. Now we'll go to the solution of equation. First thing is a rank of a matrix. So whatever the matrix given, you take the determinant, and if the determinant is equal to 0, that means the size is equal to, or is rank is equal to less than the size. Okay, here it is a 3 by 3, and if the determinant is equal to 0, that means there is a linear combination of rows. No, so that is here it is also coming. So the row is the determinant is equal to 0. That means the rank is not equal to 3, it is less than 3, or its rank is less than the size of the square matrix. Okay, so which is equal, it will be less than that. You have to also check whether it is equal to 2 at least. So for that, look for any uh, this 2 by 2 content with non-zero rows. Okay, so definitely there is still a non-zero content available. So for the 2 by 2. So that means this rank is equal to 2. Okay. And now the solution of equations, only two different content. So solution of linear algebraic equations. Okay. So we are given with the three equations. We have to say about whether there is a unique solution or no solution or infinite number of solutions or only the trivial solution. Okay. So this is of the form Ax equal to B. Okay. So to say about the solutions, first simply get the rank of the matrices A as well as A and B. There is as augmented matrix. Okay. So rank of A and B, A and AB, we can check it together simply. So make the augmented matrix. Okay, this element of this augmented matrix. So we'll come to this. So and do some operations and check for this rank, get the rank. Okay, so here these two this row 3 and row 2 or is the row 3 can be easily made as now 0. So row 3, there is this content can be subtracted with this, so that this is made as 0. So row 3 minus 2 are 2. So by that way this is coming as 0. So what is the meaning of this? Actually, this x1 plus x2 plus x3 or is 0 x1 0 x2 plus 0 x3 equal to 2. So that means for nothing we are getting some entry. That means here the equations are inconsistent. Okay. So definitely, you should not get this way. For nothing, we are getting this right side is coming as a positive content, some content. So that means that, of course, you can easily say that rank of this 3 by 3, the original matrix is only 2, whereas the rank of this augmented matrix, which can be taken as this way, which is actually coming as higher than 2. So rank of A and rank of AB, if they are equal, okay, we can get some solution, but here these two are different. Okay, so this rank of A is less than rank of AB augmented matrix. So which is, of course, this is equal to number of variables. So here no solution is possible because here for nothing we are having something. So what is the meaning of that? No, that means inconsistent equations. So let us see the rules now. So if the rank of A is also equal to rank of AB and equal to number of variables, then unique solution is possible. That's what is normally we are aiming for. Sometime we also end up with this. So rank of A is less than rank of AB, which is equal to number of variables. So here no solution is possible. Suppose this rank is still equal, but they are less than the number of variables. So in that case, you'll be getting infinite solutions. Maybe one of the thing you can keep it as a parameter according to which the other two variables can be set about. So otherwise, you'll be having many solutions, infinite number of solutions. So unique solution, infinite solution, okay, that is something. Whereas this is no solution, that means inconsistent equations. Okay, only this thing. A related problem, of course, a similar one here. What we are getting is a matrix and AX and B. Okay, the same way. AX equal to B. What we are doing is this operation for the augmented matrix. We are trying to get the row operations, and we are seeing this A matrix and AB matrix. Both are now having this entire row thing is turning as 0. That means rank of A as well as AB is simply equal to 2. But number of unknowns are only number of unknowns are 3, x, y, z, or this x1, x2, x3. So there are 3 variables connecting only 2 equations. So infinite solutions are possible. So you can fix, say, like suppose this is of course this is y and z. So y and z, if you fix this z value to one thing, accordingly you'll be getting a y value, and using that you'll be getting a x value. So you'll be having, according to the value of z, you'll be getting the other values connected. So you'll be having infinite solutions. For infinite solutions, uh, this is a condition. Rank of A and B are less than, of course, this thing has to be first matched. This rank of A should be equal to rank of AB. Okay, and it has to be less than the number of unknowns. So 3 unknowns are there, only 2 equations are there. So that is the meaning of this. Okay, 2 independent equations. So in that case, you'll be having infinite solutions. Whereas here, there are 3 equations still available. 3 equations, of course, one of the equation doesn't have any meaning. So now for nothing, we are having other thing. So otherwise, this is having this inconsistency that rank of A is not equal to rank of AB. Okay. So this condition is having because of some mistake. Okay, this is inconsistent equation for which no solution is possible. Okay, and there are examples given. You can also go through. For example, this 3 by 3 matrix. You can easily solve this using our matrix inverse. No, or it is like AX equal to B. To get the X, simply A inverse into B. So this you can easily do with your matrix in Excel. Okay, you can have got this solution. So this is a unique root. Here, rank of A and rank of AB are different. So you can also see that. Say for example, if you add this 2 and 3, so we'll be getting this another equation. That is first equation as such written, and 2 plus 3 if you write, you are getting another equation. So you can see this pairing us that both the left hand sides are the same, but right hand sides are different. So that means these 2 equations are inconsistent. Okay, there is no solution for this. Correct? No. So this is one. This is giving 6, and another is giving the same different. That means this is a inconsistent equation. Here no solution is possible. Here unique solutions. Okay. That is rank of A is less than rank of AB. And here we have both the things. Of course, if you solve this, of course, here this one equation as such you have it, and this 1 plus 2 if you add, you have another equation. So 1 and 2 added. Okay, by that way we have equation, and that is simply resulting as equation 3. So 1 and 2 and 3 are the same. Of course, we have 2 distinct equation now. Equation 1 as such, and equation 3 as such is simply the 2 plus 3. Otherwise, out of the 3 equations, only 2 equations are independent. So one of the equation, that is this equation, you can easily get simply by the combination of the other. So that means 2 equations connecting 3 variables. So you can have infinite solutions. So that means you can fix either one of the parameter, and other variables can be related in terms of the fixed parameter. Okay. Now we'll see this homogeneous equation. Is under what condition we'll be getting non-trivial solution. Okay, for the value of A, for which value of A we'll be getting non-trivial solution. So for that, first let us write this as such. So AX equal to B. So this is a homogeneous equation. So for homogeneous equation, these elements are simply 0. Okay. Here the x equal to 0 is a by default a solution for these equations Ax equal to B. Of course, what is the usage of that result? No, what is called as that is a trivial solution. That means insignificant or not so useful solution. So we normally we look for a solution which is having some meaning. That means not full of zeros. So for getting this x not full of zeros, for that thing to be coming. So this again we'll look for this determinant of A if it is less than of course if the rank of this 3 by 3, of course rank of the 3 by 3 matrix is less than 3, then we'll be getting this what is it, infinite solutions. Of course the x equal to this is already 0 0 is a valid solution, but that doesn't have any usage. What is called as that is a trivial solution. Non-trivial means significant solution. Trivial refers to not so important. Okay. Of course, sometimes this Tamil medium student, I from Tamil medium, I felt it difficult to understand this meaning of trivial. Trivial means not so important. So we are looking for non-trivial. That means significant solution. So the significant solution for getting that, this determinant of this A, if it is 0, that means the rank of this given matrix is less than the size. Then at least one variable we can fix, the other variable can be related. Say for example here, for the value of a equal to 8, we will be getting this rank will be less than 3, or is the determinant is 0. That means out of 3 equations, only 2 equations are independent. Okay, 2 independent equations are there, 3 variables are there. So 2 equations and 3 variables means you can fix one of the variable. Okay, and the other 2 variable can be related in that. So by that way, we will be getting infinite solutions. Okay, for this homogeneous equation, always we look for normally infinite solutions only, out of which if the determinant is simply coming as 0, sorry, if the determinant is not equal to 0, that means this only 0 is the solution. If the determinant is equal to not equal to 0, that means rank is 3. There are 3 variables, means 3 equations are there, they are connecting. 3 independent equations are there. So for that, the only solution is simply 0, 0, 0. The only 0 is the solution for this ax equal to 0 with a equal to the with rank of a equal to the size of the matrix. So what we are looking for is rank of a should be less than the size of the matrix. Only then we'll be getting non-trivial solutions. Non-trivial means not significant solutions, for which we'll be having root other than 0. Okay. For x equal to 0, x equal to 0 is a trivial solution for every set of homogeneous equations. What we are looking for is x not equal to 0, or some meaningful better roots. So for that, this determinant is to be equal to 0. By that way, we are this 3 by 3, out of 3 by 3, we are now having 2 equations connecting 3 variables. So we are, by that way, we will be getting infinite non-zero solutions. Okay, with this done, of course, this also related, you can go through nothing. The similar thing in terms of statements, it is available. You can go through this. So always again saying to say like, under what condition we will be getting non-trivial solutions. So for getting non-trivial solutions, determinant of A has to be 0, and as well as rank has to be less than the size. So A and C are the correct statements.